Okay, we'll wait for 5 minutes. Let's see if anyone joins, then we'll start. Okay, anyway, start. So this is week 3 of NOC EE-62, Basic Electronics. The instructor is Professor Mahesh B. Patel from IIT Bombay. I am Debashish Nandi from IIT Kanpur. I am a TA to this course. So as you know that we go live every week 3 to 5 for this live tutorial session, right? So again, I'll reiterate the prerequisites that I would expect you to go through the previous week lectures and at least attempted the assignments once so that you can follow the tutorial easily and it will be helpful to you. These are the regular decorum you should maintain, and also I would request you to be present with a scientific calculator, so it will be helpful so that you can go to the calculations and go with the calculations as I am doing, right? So you can follow. So this is week 3. Let's begin. So today we'll be discussing basically the diode circuits, right? Some part of the diode circuits. These are very simple, but I will be going very basic and very slow. So let me first introduce you to the what a diode is, right? So I can see 3 means only Gunjan Patel has joined. Yeah, I think the audio should be fine. If you have any issue with the audio or the slide presentation, let me know, right? So let me first discuss what a diode is. So we will be discussing diode circuits, right? So diode, right? What a diode is? A diode basically, diode means a two terminal device which allows for current to flow in one direction. Current to flow in one direction, right? So general way to make a diode is, we know that is a PN junction, right? So I am not going into the device physics because that will be a totally different lecture. And also, if time permits, today I'll show you some basics of the band diagram, right? How to draw band diagrams. So this is a diode symbol, right? This is your P side, this is your N side. And if I show you the device point of view, so this is your metallic junction, this is your P side, this is your N side. So in P side you will have acceptor ions and inside you will have donor ions, right? This is called a barrier, or you may also refer it to a depletion region. So what diode does, when you apply a positive voltage, then current flows this way. But when you apply a negative voltage, then the current path is cut off, right? Basically, there will be a very small amount of current that is called reverse saturation current. But for our course, we don't consider that. So the way diode works, if I draw the IV characteristics, I means current flowing here and V means this voltage, right? Let's assume N is grounded. So the way diode works is, you need to apply certain voltage, which is called cutoff voltage or built-in voltage, then it starts conducting. So if you see the diode characteristics, it will be like this: exponential V voltage applied by eta Vt minus. Let's not worry about these terminologies right now, right? This will not be so much important to us for this course. So how will we simplify this? We simplify this model as, we assume this is generally 0.7 volt for silicon diode, right? So we assume that before 0.7 volt is across the diode is cut off, or there is no current through the diode, or it is an open circuit. And when there is 0.7 volt, there is a huge amount of current flowing, right? So it pins the voltage across the diode to 0.7 volt. This is called your, let's call it IDVD, right? It will be better. This is ID, and also this side, this side there will be very small current, so we can assume that this is, I'm not showing the breakdown or anything. This will be, this is called reverse bias, this is called forward bias, right? When your voltage across P to N terminal is positive. So this simplification is called constant voltage drop model. Okay, and how this is you can say actual to a zeroth order, not zeroth order, to a first order approximation, let's say, or approx, and your circuit will be, in both case it will be this. For this constant voltage drop model in forward bias, when VD is greater than 0.7 volt, then we can model this diode as a voltage source, right, of 0.7 volt. And when in reverse bias, let me add another page. And when in reverse bias, or VD less than 0.7 volt, then you can model it as an open circuit, right? This is a constant voltage drop model. Next, a further simplified version would be an ideal diode, right? What do we mean by an ideal diode? Ideal diode does not consider about whether there is any built-in voltage present or not, right? It simply says that if it is in forward bias, then it will conduct. If it is in reverse bias, it will not conduct. So the model becomes, this is the model, right? This is the curve. So in ideal diode model, if it is in forward bias, then we just simply use it as a short circuit, right? This is AB, AB, it is a short circuit. And in reverse bias, again similar to the last case, it is an open circuit, right? So for this tutorial, we will be using this model, constant voltage drop model, right? Again, please note that when voltage across this is the positive terminal, this is the negative terminal, P and N, voltage across P and N is more than 0.7 volt, then we will replace it as a constant voltage source, right? And when it is less than that, or the diode is in reverse bias, we will treat it as an open circuit. Okay, so this is all what we require for this tutorial to go on, right? So let's move on to the problem number 1. What does it say? A circuit is given. Just let me zoom it a bit so that. So what does it say? Which of the following plots correctly describes the V naught? V naught is across these two nodes, right? It is also a node. Remember that. So your VD is across this. and also there will be some drop across 2K. Versus describe the V naught versus Vi relationship for the circuit shown in the figure. Numbers such as this indicate the slope. Okay, so how do we proceed for this kind of problem, right? The approach would be, see, the approach would be, let's say, you can assume actually, right? Diode acts as a switch, as you have seen here, that under one condition it is on, actually it is conducting, or the switch is on, you can say. It is more evident from this that this is switch is on and this is switch is off. Similarly, here switch is on with a zero point 0.7 voltage drop, nothing else, right? So here two cases can be possible. Either the diode conducts or the diode doesn't conduct, right? So let's assume first that the simpler case, the diode doesn't conduct. So the diode is off, let's say. How will my equivalent circuit look like then? My equivalent circuit will look like this, right? So this is your V naught, this is open circuit, this is Vi, this is 1K, this is 2 volt, this is 2K, right? So what is your V naught in terms of Vi? It is nothing but Vi minus 2 volt, right? This is open circuit. This is open circuit. So only this loop is considered, right? This loop. So let's remember this. Then let's assume the diode is, see, why do we need to find VO versus V naught versus VI relationship? Because we need to find out the plot between V naught versus Vi, right? We need to check the slope, right? See, here we can see that the slope is 1. Is that okay with you? The slope is 1. I think it should be fine. It is a straight line, right? Then when the diode is, let's change color. When the diode is on, right? So what is the condition for the diode to be on? First case, this VD should be greater than zero point 0.7 volt, right? Understand this very carefully. VD should be greater than zero point 0.7 volt and the current conducts in this direction, right? So current also conduct through 2K kilo ohm resistance in this direction. Let the current be I. So your, what is V naught now? V naught is equal to 2I plus VD, right? So if your VD is greater than zero point 0.7 volt, then your V naught should be greater than, see, I is positive, right? Because the diode conducts in one direction only. So your V naught should be greater than zero point 0.7 volt. Can we say this? Because this quantity should be positive. So if V naught is greater than zero point 0.7 volt, can we say something about Vi? I think we can, because minus Vi minus 1I minus 2 volt minus V naught is equal to 0, right? Then Vi minus I minus 2 minus V naught is equal to 0. That means your Vi is equal to 2 plus V naught plus I. Again, your I is positive, so your Vi should be greater than 2 plus Vi should be greater than 2 plus V naught, and 2 plus V naught, V naught is greater than 0.7 volt, so Vi should be greater than 2.7 volt. At least it should be greater than at least it should be more than 2.7 volt, right? Then only my diode will be in forward bias. Now let's consider the forward bias condition. How the circuit will look like. In forward bias, we have seen that it is nothing but a voltage source, right? This symbol you might confuse. So let me draw it this way. So this is Vi, this is 1K, this is 2 volt, 2K, this is your 0.7 volt, right? Then what is your Vi? Vi minus, let's see, I is flowing. So series 2 Vi minus 2 minus 3I, because 3 kilo ohm resistance in series, minus 0.7 volt is equal to 0, right? So your Vi, just let me add a page. So your Vi is equal to 3I. Vi is equal to 3I plus 2.7, right? That means your Vi is 3I plus 2.7. Let's remember this. What is your I? You can write I as I is nothing but the same current flowing in this path, right? And this is your V naught. What is this voltage? This voltage is 0.7. So voltage drop across this is V naught minus 0.7 divided by 2, right? Let us replace it here. We get Vi is equal to 3 into V naught minus 0.7 by 2 plus 2.7. So if I just change the side, it will be 2 by 3 Vi equal to V naught minus 0.7 plus 2 by 3 into 2.7, right? So if I do this, plus 0.7 minus 2 by 3 into 2.7. I am not concerned about this part, right? Because I just want to see what is the slope. So I can clearly see that the slope is 2.3 and here the slope is 1, right? So I can write that slope here is 2 by 3, right? Now let's go to the options. These are the options given, right? So when diode is on, that means when Vi is at least greater than 2.7 volt, slope is 2 over 3. When diode is off, slope is 1, right? So first option, let's see. First option, when diode is on when Vi is more than 2.7 volt, right? And the slope is 2 over 3. So this option is not correct. This option is not correct. So we have one option A and another option D. So in the off state we have 1. In the on state we have slope 2 by 3. But the difference between is where does it cross the Vi axis, right? When that circuit has become on. We can see that in this case it is Vi is negative, but that is not possible. We have calculated that Vi should be greater than 2.7 volt for the diode to be in forward bias. So D is the right option, right? Now, can you please unmute and tell me whether you have understood this completely or you want me to explain any part? Anyone?
Understood, sir. Understood,
Understood,
sir.
right? Okay, fine. So then if this is understood, next few problems will be a piece of cake, right? So let's move on to the next problem. So it looks similar, but what they have changed the voltage direction, right? Similarly, the treatment can be done in the same way that if let's say first diode is off. If your diode is off, right, then what happens? Then your circuit becomes this, because this will open circuited. So this is your V0, this is Vi, this is 1K, this is 2 volt, right? So if I apply KVL, then it becomes Vi and no current is flowing. So Vi plus 2 is equal to V0, right? Let's mark it as equation A. Then let's check when diode will be on. Diode is on. The condition for this, similarly, your VD has to be greater than 0.7 volt. Current has to flow in this direction. So potential drop across this 2 kilo ohm will be positive. That means we can say V0 should be zero point 0.7 volt. If V0 is zero point 0.7 volt, then Vi plus 2 must be greater than must be 1 second. If V0 is this, then what is the relation between V0 and Vi? Your Vi should be greater than zero point 0.7 minus 2 volt, that is greater than that is or minus 1.3 volt. So diode will be on when Vi is greater than minus 1.3 volt. Okay, then okay, now let's draw the equivalent circuit. And diode is on. My circuit will become, this is ground, right? So this will be your Vi, this is 1K, this is 2K, this is 2 volt, zero point 0.7 volt, and this is your V0. So how do we write Vi minus Vi plus 2 volt, Vi plus 2, let's say current is I, so minus 3I minus zero point 0.7 volt is equal to 0, right? So your Vi will be 3I, this is minus 1.3, right? So what is your I? I is nothing but current flowing in this. So Vi is 3 into V0 minus zero point 0.7 by 2 minus 1.3. So your V0 will be 2 over 3 times Vi, and this is 1.5 to This will go to this side, so it will be plus 0.7 if I multiply it by 2 by 3 and plus 1.3 into 2 by 3. This we don't care about. So your slope is, again it is coming out to be 2.3 when your diode is on. Here your slope is 1, right? This is your output, this is your input. So again, going to the options. So diode on when Vi greater than 1.3 volt, slope 2 over 3. When diode is off, my slope is 1. So the curve seems similar. The higher one would be 2.3, right? And this seems to be the right option. Here Vi is around 1.3, minus 1.3, so it is also matching. And beyond this, it is diode is on. Here diode is on. Here diode is off. So this takes care of the problem number 2. Then moving on to problem number 3. This is also similar, but what they have changed is the polarity of the diode, right? Note here. Earlier, the diode was in a other facing the other way, right? So how do we take care of this? The strategy remains same, right? So first, again, let us take your diode is off. When your diode is off, then your V naught will be equal to Vi minus 2, and your diode is on, right? Now the question is, when will your diode be on, right? Your diode will be on when your this voltage VD will be, let's define it the other way, it will be easier for you to understand. This VD will be greater than 0.7 volt, right? And what is the relation between V naught and VD right now? V naught is 2, and let's say I is flowing in this way. Okay, so your V naught will be minus 2I minus VD, right? So your I is now positive because current has to flow in this way. So if VD is greater than 0.7 volt, that means V naught has to be less than minus 0.7 volt, right? Is that okay? V naught has to be less than minus 0.7 volt for the diode to be in reverse bias. Sorry, the diode to be in conducting, right? So now let's see the equivalent circuit. So for that, your Vi, what is the constraint on Vi? Can you tell me the constraint on Vi? Anyone?
It should be negative.
No, or negative by how much? What should be the value?
1.3.
How do you tell that?
I just need to think it over.
No, you are telling the answer, right?
Because one end is of this diode is at 2, the negative end,
Okay,
if I consider it this way. So to make it forward bias, this should be at least 2.7.
2.7.
For this to be forward bias, if this negative terminal is connected to the 2 volt, which is again negative. Yes, so this is negative 2 volt over here, minus 2. So to make it positive, the VD will be the V positive minus V negative. If I
Right,
talk in
but let's do it more simpler way, right? See, we
okay,
know that this is, let us apply KVL here, right? The question I'm asking this, the reason I'm asking this, because see, now say it is a V naught, right? And it is your Vi. Your current has to flow this way, right? In forward bias. This is just a convention. Not, don't follow this one. If the diode is in forward bias, the current has to flow in this direction. That you agree?
yes,
So if this is your 2 volt and this is your I, so can I write KVL here? Your Vi minus, let me make it more simpler for you to understand, right? Let's say this is V naught, this is Vi, and the current is flowing in this direction, right? So your Vi is minus 2 plus, then again it is minus 2 plus 1I, then again plus 2 minus 2, then again plus 2 minus, right? Minus V naught is equal to 0. So your V naught is equal to Vi minus 2 plus I, right? So if your, so V, what is your Vi? Vi is equal to V naught plus 2 minus I plus, is it right?
the 2K with the diode you are, I think, missing.
No, no, because I am taking this is V
Replacing
naught,
it
right?
by V naught. Okay.
Yes, this entire
Complete V
stuff
naught.
is V naught, right?
Okay.
So what is your Vi? Vi is nothing but V naught plus 2 minus I, right? Then we know the condition on V naught, we know the sorry, this was, we know the condition on this, right? V naught should be less than minus 0.7. So Vi should be less than 1.3 volt, right? Is it clear? V naught is minus zero point 0.7 volt, less than minus zero point 0.7 volt, then only my diode will be in forward bias. From this, can we say that Vi to be less than 1.3 volt for it to be forward bias? I think we can say, right? This is zero point 0.7 if I put, right? Then it is evident that, and for the time being, let's say I is 0, right? Then we can say that Vi should be less than 1.3 volt. So we know the condition on Vi. Now, sorry. Now, if we just look at this circuit, right? This circuit, then can we find out the slope? I think we can. And the way would be just simply applying the KVL minus 3i minus 2, and this would be your plus zero point 0.7 is 0, and your I would be this. So sorry, Vi is your 3i and some constant stuff, right? Let's call it C. Because we don't care about that right now. Equal to 3 into what would be your I? Your I would be nothing. This is V naught. Then V naught plus zero point 0.7. V naught plus zero point 0.7 by 2 plus some constant, right? Then again, if we multiply it by 2 by 3 on both sides, it becomes this plus 0.7 plus 2 by 3 C. So if we see V naught 2 by 3 Vi, and then you see some constant terms. So here we can see the slope is 2 over 3. This case when diode is off, the slope is 1. Now the question is when the diode will be on. The diode will be on when Vi is less than 1.3. So if we go to the options, so if I just simply draw it, this is V naught, this is Vi. So beyond certain voltage around 1.3, it is not exactly 1.3, right? It is around 1.3. Beyond certain voltage, diode is on. So your slope would be 2 over 3. And this side, your diode is off. And your slope would be around 1. Not around 1. Slope would be exactly equal to 1. So if you just see from the options, right? So this line will be much steeper, and then there will be 2 by 3 and this. So let us find out for this shape. We have option, this is not right, not right. We have option B and option A, right? But we can see that option A would be suiting us because the range of Vi for which the diode is on is less than certain positive voltage, around 1.3 volt, right? So this will be the right option. Okay, so let's remove this part. Okay, so let's move on to the next problem, and I would ask you to unmute yourself and please assist me to solve it, right? Please tell me the steps so that I know that you have got the steps which I have explained in the last three problems. This should be a similar, yes, this is a similar problem, right? Just the change in opposite battery sign. Uh, you can see Gunjan and Poonam. Any one of you, please unmute yourself and uh, tell me how to solve it. It will be a good practice for you also.
When the diode is off,
Okay, just you tell me, I'll write along with when the diode is off. Okay, then
then
what happens?
V naught is equal to
V naught is equal to
VI plus 2 volt.
VI plus 2 volt, right?
So
So
I think
the slope
this
is,
is exactly the same way which was in the previous case.
yes, right. The slope is
1.
1. Fine. Then when will the diode be on? Let us go step by step, okay?
Right,
So first let's put the condition on diode voltage. So my VD should be greater than 0.7 volt, right?
right.
So my V naught should be, look at the polarity, right?
Le- yeah, yeah.
So my V naught should be,
Less than 1.3.
no, no, V naught,
V
this.
naught. Okay, so V naught will be VI,
See, let's do it. V
uh,
naught is, current
VI,
is flowing in this way, right?
right,
So this is the potential drop here, 2I, right? In this direction. So V naught is
right.
minus of
Plus,
2I
2I
plus
plus VD.
VD, right?
Right, right, right,
So my I is a positive number. So this entire term is some positive value, right?
right,
So I do not know I for the time being. So my V naught is some negative value minus VD, right?
VD.
And I
Right.
know that my VD should be less
Greater
than,
than
no, sorry, my VD should be greater than zero
point 0.7.
point 0.7 volt, right? So my
Right.
V naught should be less than minus zero point 0.7 volt.
Okay.
Okay,
Right.
just let me tell you another way. Let us think that this I is not present, okay? Let it be 0. So your V naught is minus VD, let's say for the time being, okay? If your
Right.
VD is greater than zero point 0.7, right? That means your minus of V naught is greater than zero point 0.7,
Right.
okay? Just we flip the signs.
Okay.
Just change it this way, right? This goes to here, this comes here. So this becomes your V naught, this becomes your minus zero point 0.7, right?
True.
So your V naught is less than minus
Less
zero point
than
0.7,
point 0.7.
minus zero point 0.7, right? This is a
Right. Right.
minus sign, right? This way we can check. So your condition on V naught is less than minus zero point 0.7 volt. What is the
Right.
condition on, what is the condition on VI? You can simply tell from here only.
VI is V naught minus 2.
Vi is V naught minus 2, right? So your
Right.
Vi is V naught minus 2, your V naught is minus
Minus
0.7, less than minus 0.7, so Vi should be less than
1.2.7.
minus 0.7 minus 2.7,
2.7.
right?
Right.
So this becomes my condition of on Vi for the diode to be on. Now just do the equivalent circuit analysis. Again, for the simplicity, let me do it in this way. This is one, there we have a battery, there we have a resistance, and here we have a battery. This is your 0.7 volt. Current is flowing this way. This is Vi, this is 1, this is 2, this is 2K, right? So if you do the nodal analysis again, it becomes Vi.
Plus I.
Let's take the current in opposite direction, it will be easier. It doesn't matter actually, but it will be easier. Vi minus
Minus I.
I
Plus 2.
plus 2
Minus 2I.
minus 2I
And minus 0.7. Plus 0.7.
plus 0.7, right? So your Vi is nothing but 3I minus, let's take this some constant, 3I. So what is your I? How can you relate I to V naught?
V naught is I V naught.
How can you replace I in terms of
V
V
naught
naught?
minus 0.7 by
V
2.
naught,
Minus 0.7.
is it minus?
V naught plus minus
V naught, this is, see, suppose
reverse.
this is 3 volt, this is 2 volt, right?
Right.
And there is a resistance.
3
What is the
minus 2.
current flowing? And if
3
it is
minus
minus 2, then what happens?
3 plus 2.
Right? This is nothing but
Right.
a battery. I can simply write this as this minus 0.7 volt.
Right. So minus minus becomes plus. So V
Yes.
naught plus
So it is V naught plus zero point
plus
0.7 volt,
points.
right? So what is the slope here? You can easily see that your slope is V
2
naught
by
plus
3.
0.7 plus minus 2 by 3C. Yeah. So this is your constant. What does this constant define, by the way? Just let me come back to that later. Some constant. So your slope is, this is your y, this is m, this is x. So this is slope is m equal to 2 over 3, right? So your answer is, see, let us draw the tentative graph. V naught, V in. First we check that slope 1 for off, and when it is off, when it is more than around 2.7, right? It is, let's say it is around minus 2.7. So this way it is off, this way it is on, right? So your plot will something, when it is on, then it is this slope 2 over 3, and suppose it is on, then it is 1. So we'll look for this curve, this kind of shape. So this is not right, not right, not right. This seems to be right, B. And also we can see that it is some negative value. So this is your diode on and this is your diode off. Okay, now tell
Right.
me uh, what is the significance of this constant? What will it change in this curve?
Actually, I think governing the bend point, whether it is in quadrant 2 or 3.
Yeah, right. You're absolutely right. Whether this point is here, because this can also be a possible solution, right?
Yes,
So this point is determined by this. So there are some more boundary conditions needed to find this out. Okay. Our
right.
question does not demand that. It just demands that whether it is, you can check by just inspection whether it is which solution is there, right? So okay, you can mute yourself. Thank you. That will take care of problem number 4. So let's move to problem number 5. In this circuit shown in the figure, Vi is increased starting from 0 volt. So at what value of Vi the diode will turn on? This plot, have you seen somewhere? I think I have just mentioned at the starting, right? This is the constant voltage drop model. This one. See, it's the same thing. At the instant when you have zero point 0.7 volt, your diode starts to conduct. It's in the forward bias, right? It's in the forward bias and it's on basically. So you see, not for this course, and you should remember this, that if two plots are met, right? If two curves are met some point, let's say this is a curve, uh, this is a boundary somewhere, and from here it is a straight line. This is f of x, f1 of x, this is f2 of x, this is f of x, this is x. So you may note that at this boundary, right, both this equation and this equation, it should satisfy. Then only there will be a single point, because at this point this solution is also satisfying, this solution is also satisfying. It is the same case, right? Suppose we have a step function. We have a step function, or basically the change in slope. At this point, there is a discontinuity, right? So here also there is a discontinuity in slope, because if you see, one slope would be like this, another slope is like this. So the slopes do not match, or the first derivative do not match. So in these conditions, you should remember that this state and this state converges at the same point. So both the conditions should satisfy. So let us keep this in mind and move forward to solve the problem. So first thing, when the diode is off, right, they want us to find out what will happen if, at what voltage this diode will turn on. So basically turning on or turning off of diode happens based upon the voltage across it. Okay. So let us define this node voltage as VA and this node voltage as VB. So when my diode is off, then my circuit becomes simply this, right? This is your VB, this is your VA, this is 2K, this is 1K, this is your VI, right? So what is your VA at this point? let's say it is a common node ground. Your VA is nothing but VI into 2/3, right? And your VB is nothing but 0 volt. Now, when the diode is on, then what is the situation? It is nothing but a 0.7 volt drop, right? This is your VB, this is your VA. So, this is your 1K, this is your 2K, this is your, what was it, 2K. So, if we apply KCL at node A, right, then what do we find? VI minus VA over 1 equal to VA over 2 plus, what is this voltage? This current in this branch is nothing but VB minus 0 over 2, right? So if you solve this, it is VI is equal to your, this is VA plus VA by 2 plus, what is your VB? Your VB is nothing but VA minus 0.7 over 2. So let's add a page. So VI became, this is half, this is 2 VA, and this is minus 0.35, right? So I need to find out at what voltage my diode is turning on, right? So at this stage, can you just tell me what is the junction point? Junction point means this is two states, right? This is one state of the diode voltage. This is one state of the diode voltage. So what are the condition on VI? How VI will merge to each other?
So the question is not clear.
The question is that we are asked to find out that at what voltage of VI the diode will be on, right?
Right.
So first we are analyzing that when the diode is off, then what is the node voltages VA and VB. Now we are analyzing what is the condition when the diode will be on. Then we need to merge them together, right? Because at the same instant when this voltage switches, my diode changes from on off to on state.
I got your point.
So my question is, can you tell me how can I find the constraint on VI?
In both the cases, we'll have to find when diode is on and off, and then equate the
Okay.
two.
Mm-hmm.
Because as long the diode is off,
Okay.
then VA should be less than that value which turns it on.
VA should
So
be
less than the 0.7 volt, because VB is at 0 volt.
right, right.
So when as long as VA is less than 0.7, the diode will remain off.
So if I got you correctly, what you mean to say, this is 2VA minus 0.35. So what is VA? Can you tell me what is VA at this point? This is nothing but VB plus 0.7,
Yes,
right?
right.
So how can I put the constraint same for both the cases?
So, as from the first condition, when the diode is off,
Okay,
it will remain off till VA, the node voltage VA is less than 0.7.
right. So
But the moment
basically,
V,
if I rephrase it in a different way, that in this case, if you make VB is equal to 0, right?
okay,
Then can we approach to this condition,
oh, yes,
right?
right,
Because at the instant when the diode gets switched on, my
got your
VB
point.
is same, right? For both the cases, because it is the same thing I was explaining earlier also. At the boundary, both the conditions should match. Now I need to find out any variable through which I can make that possible, right? So here if I put VB equal to 0, then this becomes my VI becomes 1.05. So see what happens. Suppose I am increasing VI, right? Till it is 1.05 volt. My circuit will look like this. Fine. Now, as soon as I am at Vi equal to 1.05 volt, there my circuit looks like this. But at the same instant, at t equal to 0, let's say t equal to t0 minus and t0 plus, both the values should converge to a point or meet to a point, right? So my Vb at that instant remains 0, and putting on the constraint on Vb, I can calculate my Vi. So my Vi is coming out to be 1.05 volt. So the correct answer would be, let me see first whether it is present. 1.7. Oh, yeah. C is the right answer. Okay. Okay. So moving on to next problem. Oh, same circuit. But they have mentioned that Vi is 5 volt, right? That means we know that the diode is on, because we have found out that at 1.05 volt of Vi, my diode will be on. So now it is 5 volt. So the diode should be on. So my circuit will just look like the case when my diode is on. And when the diode is on, from this concept, when the diode is on, irrespective of what voltage you apply, the potential across your diode will always remain zero point 0.7, right? Irrespective of whatever the current is flowing through it. See, from this plot, if I take these 3 points, current is changing, right? But my VD remains same, because this line is a parallel to y-axis line. It is just like a constant voltage source, right? Nothing else. That's how, and that's why actually in the circuit analysis you replace it with a constant voltage source. This is the logic behind it. This curve. If the curve is like this, right? You cannot do that. Do you get me?
Yes, sir.
So it is 1K, it is 2K, it is 2K, and it is Vi. This is R1, R2, R3. They want us to find out V3. Okay, fine, V3. So we have designated this VA, this is VB. So they want us to find out VB basically. Okay, we can just use KCL at node A. Vi minus Va over 1 plus Va over 2 Va over 2 plus Vb by 2. So Vi is 5 volt. 5 minus Va by 5 minus Va by 2 plus Va minus 0.7 by 2. That means 5 equal to 2 Va. This becomes minus 0.35. Va is 5.35 by 2 volt. So what would be my V3 or VB is nothing but 5.35 by 2 minus 0.7 volt. That comes out to be, if I not approximate, let's calculate it. 2 minus 0.7 times 1 comes out to 1.975 volt. So okay, the option is not here, so we can closest approximation would be 2 volt, right? So moving on to problem number 7. I think it is the same. Yes, it is the same circuit, and they want us to plot. No, they want us. Yes, they want us the slope of V3 versus Vi at Vi equal to 5 volt. So this part at Vi equal to 5 volt, we will convert the circuit to diode on condition. We take care this from that case. Let's quickly draw the circuit. So this is my V3. This is 2K. This is 2K. This is 1K. This is not Vi, because I need to find the plot between V3 and Vi, and this is my 0.7, right? So from the last analysis, sorry, rainy session, okay, if I just simply follow the last plot, then we get Vi, let's say it is Va, this Vb. Vi minus Va by 2 is equal to Va by 2, and then we get Vb by Vb, let's say I need to V3 by 2, right? So Vi by 2 is equal to Va plus V3 by 2. That means my Vi by 2 is becoming Va plus this is,
Wrong.
sorry, this is,
Vi minus Va is 1K.
yeah, right. Yes, this is 1K, this is 3 by 2, this becomes V, just hold on a minute. VA is my V3 or VB plus 0.7 plus V3 by 2, right? Then my VA. Can you please mute yourself? I am not sure. It is a rainy session. Okay, right. So if we just proceed here, then it is 2V3 plus 2.1 by 2. That means my V, what is the V3 versus Vi plot, right? V3 is equal to 1 by 2 Vi plus 2.1 minus 2.1 by 4. So the slope is 1 by 2, right? The slope is 1 by 2. So D is the right option. Okay, let's move on to the next problem. It is on, okay, there is a Zener diode. So let me first tell you what a Zener diode is briefly. Zener diode, if you see an idea in real diode plot, you'd see the IDVD characteristics would be like this, right? This is the reverse bias region, and around this point we tell that this is the VBR, breakdown voltage. The diode breaks down because the junction breaks down and high amount of current flow. So if for Zener breakdown, what happens? This almost remains same, and this becomes like this. Okay, so this point we call it VZ, V Zener. So can you see a similarity with the forward bias situation, that here your voltage is getting pinned at this potential, right? If I just idealize the circuit, how Zener diode plot in a constant voltage drop model look like is this. This is your 0.7 volt, this is your VD, this is ID, and this is your VZ, actually minus VZ, right? So what is the application? The application is these Zener diodes are used in voltage regulator circuits, right? So you can use this to make sure that potential across a voltage is fairly constant, right? So you can use it in stabilizers also sometimes. So with that concept, let's copy this circuit, and what is asked that V on is 7, Vz is -3, that means this is minus 3 volt. And what is the slope? dv0 by dvi when d2 does not conduct. Okay, sorry, when only d2 conducts. That means your this is not conducting, right? So we don't care about this, and only D2 is conducting. That means this drop you will find it to be 0.7 volt, and they want us to find out the slope between V0 and Vi, right? Because dV0 by dVi is nothing but the slope. So if I use KVL in this loop, Vi minus, let me tell it, I of 1.8, then minus 0.7 minus 3.3, I equal to 0, right? So my Vi would be 3.3, 1.8, 5.1 I plus 0.7, right? So what would be my I in terms of V naught? I can be simply written as Vi minus V naught by 1.8. So your Vi would be, did I do it right? Okay, I think I have complicated this, right? Let's do it in a simpler way. Maths will be simpler. This current should be equal to this current. Then Vi minus V naught over 1.8 would be nothing but V naught minus 0.7 over 3.3, right? So Vi over 1.8 would be V naught by 1.8 plus V naught by 3.3 minus 0.7 by 3.3. So your Vi by 1.8 would be V naught over, this would be 1 divided by 1.8 plus 1 divide 3.3. It is 1 divide 1.16. If I am not wrong, then your V naught would be 1 divided by 1.8, 1.16 divided 1.8 into Vi plus some constant term. So your V naught would be around 0.647 Vi plus some constant terms. So this should be your slope, around 6.5. So yeah, B is your right answer, right? So this takes care of that. Next problem is, in the circuit, what is the slope of this when D2 conducts in the forward direction and D1 conducts in the reverse direction? Okay, so if you see the circuit and D1 conducts in the reverse direction, That means I have this voltage as 3 volt, right? Because my VZ is 3 volt. So I can simply write the KCL at this node as no,
Excuse me,
VI.
sir.
Yeah.
So in this question, the D2 diode, the
Mm-hmm.
cathode is grounded.
D2 diode cathode is not grounded.
So it's through R3.
Okay, okay, please go on. What's your question?
And so to my mind, it comes then the anode should be at a positive potential for it to conduct.
Okay.
And for the D1 diode, which is Zener diode,
Mm-hmm.
it is a reverse condition.
Okay.
The anode of the Zener diode is grounded. So for
Mm-hmm.
it to be reverse biased, because it says D1 conducts in the reverse direction.
Right.
So the potential at this V naught should be negative.
Why so?
Oh, sorry, it should be positive because it's fine.
Right, right.
Right, right. For it to be reverse biased, so V naught should be positive. Right. So
Yeah, just let me clarify again. This is IDVD of, let's say this is for the Zener diode. This is for the PN diode. This is D1. This is D2. PN diode, not the right term. Let's say this is D2. So what are the models we are using? We are using the model for D2 is this. And for Zener diode, the model we are using is this. Okay, so in the question it is mentioned that D2 conducts in the forward direction. That means our operation regime would be this line, right? And this D1 conducts in the reverse direction. Now, can you tell me what is the in which region uh, just let in which part actually of this reverse bias D2 is conducting? Sorry, D1 is conducting.
it should be this 3 volt because it's a Zener diode.
No, why can't it be this? What do
But
we mean
in
by
this case,
conducting?
if it is here, will the D1 diode be forward biased? It will be reverse biased then.
No, no,
D
right. That is fine. But what
D2
does the term conducts mean? If I
has to
say
be
that
in.
this is conducting, that means what basically?
Okay.
No, in terms of current and voltage, you can tell me if any element is conducting, that means what?
Current is flowing through it and there is a
Yes.
potential drop across it.
Uh, Potential drop is not necessary. Suppose it is a short circuit, right? Ideal metallic wire, we can ignore. Yes, potential drop will always be there. There is no ideal element, but current should be there, right? The
Right.
main purpose is current should be there. So in this region, is there any current in
Is the
our model?
reverse?
No, no, in our model, there should be some reverse
No,
saturation current that I know, but is there any current in our model?
no.
No, right? So when does this conduct mean? It is conducting means I have to lie on this line.
Right.
Then only I have some current, non-zero current,
Right.
irrespective of the polarity, non-zero current. And if this is conducting D1, then what is the voltage across D1?
It's plus 7.7.
No, D1, Zener.
D1. Zener.
If Zener is conducting in a reverse direction, what is the voltage
Right.
across it?
Voltage across it is 3 volt.
It has to be 3 volt, right? Because
Right.
only
Right.
at 3 volt it has non-zero current. It's like a
Right.
delta function.
Right.
So I can write this term for simplicity that this is 3 volt. So I can simply simplify the circuit as follows. Do you agree with me on this equivalent circuit?
So will we show the Zener polarities the way you have shown, or in a reversed way?
No, right. This is my diode. Okay, let's say this is my
Hmm.
Zener diode.
Right.
This is my forward drop.
Right.
This is my reverse drop.
Okay.
So
So you
if
are
it
showing
is
it 3
reversed
volt.
bias, then my
Right.
this potential would be 3 volt, and this, if this is cluttered, just can you see now how this potential is, because this is my N terminal, right? And this is my P
Right.
terminal. So at
Right.
reverse bias, this should be my 3 volt.
Okay.
See, it is in the
Okay.
negative side of the axis, right?
Right. Okay.
So this polarity is fine then.
Right.
This equivalent circuit, okay. So now the analysis becomes simply a KCL one. At this node, I will use KCL again. Bi minus V naught by 1.8 K. This current should be equal to this current. This current I am finding out between this node to ground. This node voltage is nothing but V naught minus 3 over to V naught minus 3, and the current is this, plus V naught from this branch current is minus 0.7, 3.3K. So 0.8 is equal to V naught by 2.2 plus V naught by 1.8 plus V naught by 3.3 plus some constant term. So if I do the calculation quickly, 1 over 2.2 plus 1 over zero point 0.8 plus 1 over 3.3 is equal to Bi 1 point, sorry, I think I made some mistake. 1 over 2.2 plus 1 over 1.8 plus 1 over 3.3. Okay, over 3.3 is this, answer this, divided by is this. So this is 1.313 plus some constant terms. So your V naught would be equal to Vi into This is coming up to be 0.76 over 1.8 plus some constant terms. So V naught is Vi into 0.42 plus some constant terms. So this is my slope, right? So yeah, A is the right answer. Okay, so okay, this is also similar problem. I am not solving this. I'll upload the solution. And due to time constraint, let me go to the other type of problems. This again similar problem. Solution I will upload. Okay, let's discuss this problem. So what does it say? An input voltage of certain DC and some AC is applied to a circuit shown in the figure. Okay. What I observe is that there is no resistive component, so the delay is almost zero. And if V1 is zero point 0.7 volt of the diode and VI DC component is 3 volt and V in is 4 volt. VM is 4 volt. Then what is the output voltage V0? Okay, fine. So let's first go step by step and draw the waveform. And minus. Can we solve the sixth problem from the assignment? Can you unmute and explain your doubt, Gunjan?
Sir. Problems are similar, but as we solved that previous problem, but we have to measure voltage across diode. AB terminal are across diodes. That D2.
Sorry.
Across D2, that
Which?
D2, that
Okay.
VO, that node VO is
Uh-huh.
mentioned as A, and node B is A, and we have to measure that
No. This is the
VO.
this is the question.
Similar, but VO we have to measure across diode, not from ground to diode.
Okay. So what is the catch in that?
Actually, I have solved that but my answer is wrong.
Okay. Is it in this year assignment problem?
Yes.
Or
But
have you submitted the assignment?
yes, I have submitted that assignment.
Okay.
15th February was the last date, and I have submitted.
Okay.
Mm,
So your query is how can we find out right? This voltage.
yes.
And that can be easily done, right? If you know this voltage, you just subtract this voltage, right? And also you can see that this voltage won't change. Once the diode is on, then it is just
Hmm.
simply 0.7 volt.
Okay. Okay,
Isn't
sir, I
it
will
so?
try. I will try, and if I have any doubt, then I will.
No, if you
Uh,
see, if you have any doubt regarding any of the assignment problems, right?
okay.
I am not sure how does they provide this. Does they provide the answer keys or the solution,
Yes, they provide answer key. Means
and
in
they
the
don't provide
assignment they
explanation.
mentioned no without any
Oh, okay.
explanation.
So I suggest you to do one thing. You just mention the assignment number and problem number, and there is a discussion forum, right?
Okay.
You just ask me directly there, that ask telling name or asking any of the TS, any of the TS can explain that. You just mention
Oh,
that and ask them to discuss that problem in a later tutorial, or you can simply ask them to upload the solution. We can do that. We can do the
oh,
explanation and upload that, right?
okay,
Because
sir.
I'm
Okay,
not
sir.
actually quite sure what particular point you are telling. Because it is
Okay.
simply zero point
Okay.
0.7 volt if it is on, right?
Okay,
See
sir.
this curve from
Hmm.
this point, you can see that if it is in
Hmm.
forward bias
Hmm.
and
Hmm.
if it is on, then is
Hmm.
current, and current to flow, only solution is your voltage should be zero point 0.7 volt.
Okay,
Okay,
sir.
you use the discussion
Ah,
forum. I can suggest you
okay.
that, and
Okay,
we'll
sir.
surely get back to you.
Okay, sir. Okay, sir. Thank you.
Okay, so moving on to this problem, what is the okay, so this is my DC line, and because my this is DC, and over above means 3 plus 4 sine omega t, right? So 3 plus 4 would be your 7, and minus 4 would be minus 1. So your voltage will swing like this. So this is your basically input voltage, VI. So now the question is, if V on is zero point 0.7 volt for the diode, and V on is zero point 0.7 volt. Okay, V on, as usual, V on is zero point 0.7 volt, right? So see first what happens. Suppose after some voltage the diode gets on, right? For the diode gets to conducting, you can see that we need to go to the negative half cycle, right? The diode polarity is like that. Otherwise my capacitor won't charge, right? For my capacitor to charge, the should be on, and my, let me just draw the circuit, and this should be your V naught, this should be your C, and this is your zero point 0.7 volt. So what happens when the voltage is swinging? Let's say you are applying this sinusoidal at this point. Can anyone tell me at this point what is the VO? Anyone? I think there are 7
Output
participants.
will be zero,
Output will be, how do you
zero
say that?
because the diode is reverse biased,
Diode is reverse biased. Okay. And you are assuming that the capacitor does not
is
store any
not
charge,
charged. The
right?
capacitor is not having any charge.
Okay, in that case, your output is 0. Fine. Then what happens after this voltage is getting increased?
As long as it is greater than 3
Greater than 3.
in the positive
Ah,
cycle,
okay, okay, okay.
it will the output will still remain 0 because diode will remain reverse biased.
Fine.
When it goes
Below 3, let's say at this point. Then what happens to the diode?
still, I think when it will go into this minus
Minus. When it will go to? Hello? Am I audible?
now, yes, you are audible.
Yeah,
Initially, no.
yeah. Okay, okay. Some internet glitch is there. Just tell me that which point you are talking about. Here the diode will be 0, right? The output voltage will be 0, assuming that initially the capacitor is discharged.
Right.
Then
So
what would be when this point it comes to this point?
the diode will still be reverse biased.
Diode will still be reverse biased. For the diode to be in forward
The
bias,
it
right?
has, yeah,
What is the voltage required at input?
it has to go minus zero point 0.7.
It has to go minus zero point 0.7, right? Okay, just let me say at minus zero point 0.7. At minus zero point 0.7, the diode is on. Then what happens?
It's only then the current will flow, capacitor will charge.
Capacitor will charge. Capacitor will charge up to what voltage?
Uh, till 1 only, minus 1, I feel.
Capacitor will charge up to
Minus,
charge up to when my charge maximum when this voltage V in is
minus
minus
1.
1, right?
Right, right.
Now when V in is minus 1, what is my VC? VO capacitor voltage? VC or VO? If it is minus
It's
1 volt, then
right.
what is the maximum V naught?
V naught is C is di by dt.
No, 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 no.
Uh,
Just case simple. See, when I am mentioning you this no, potential between these two nodes, right? Then you
hmm.
don't see whether it is C or R. You just simply
Okay,
apply KVL here. If you apply
okay.
KVL here, you see it is minus zero point 0.3 volt, right?
Right,
Because you need to accommodate this drop also.
right.
Is it clear?
Yes, yes.
Okay. So your VO will be minus zero point 0.3 volt, right?
Right.
So my at this point, my VO is minus zero point 0.3 volt, right? So now for
True.
the diode to conduct, what should be my this node voltage?
This is minus zero point 0.3. So it can go up to,
No, not can, it has to go less than minus zero point 0.1 volt, right?
yes,
My V1 needs to be less than minus 1 volt when V naught is storing zero point 0.3 volt.
right.
Can it go less than minus zero point 0.1 volt at any instant of time?
Given the current circumstances, no.
Not current circumstances, right? So
Hmm.
after this point, My input voltage is rising. It is going the
Right.
other way. It is
Hmm.
not even going negative, it is going the other way. So my this will simply cut off. Diode will be open circuited, right?
True.
If my diode is open circuited, what is the voltage V naught?
It's negative of what is
No, the circuit becomes like this, right?
right. So
This
here it
whatever
is
you are
minus
playing,
point 0.3,
this is minus zero point 0.3. It is
point
charged
0.3.
up to minus zero point 0.3, right? Then it
Right.
is cut off. What
Right.
happens to the capacitance voltage?
It will, since this is again negative coming, it will, so no,
No, there
I'm
is no
losing
no
track.
no no there is no negative coming, right? Just
Huh.
think it this way. You have pumped current into the capacitor, it has charged up and it is storing minus zero point 0.3 volt. That's all.
Right.
Now you are
Right.
removing any other path for the capacitor to discharge. It should have
Right.
some path
True.
from where the charges can go out of the
Take,
capacitor. If
true.
it is disconnected or it is open circuited, then capacitor will store the minus zero point 0.3 volt as it is forever,
Right. Right.
right? So V naught will be minus zero point 0.3 volt for any t.
Okay.
See, again I am explaining this part. When it is here, it is reverse, right? Till here it is reverse biased diode. The circuit is off.
Right.
Here it is coming, and when it is minus zero point 0.7, then my capacitor starts charging.
True.
At minus 1 volt, capacitor is maximally charged to minus zero point 0.3 volt.
Right.
Then for the diode to keep conducting, my V in should be less than minus 1,
Right.
but it is going the opposite way. So the diode will be open circuited or diode will be off.
Right.
Then the capacitor charge, whatever voltage it has stored, capacitor voltage will remain at minus 3 volt until unless you see the path again, right? But you will never see this path because this is the maximum limit it can go.
Right.
So V in, if never goes to minus 1, less than minus 1 volt, then the diode will never conduct again.
True.
If the diode never conducts again, the capacitor will store the initial voltage as it is for
Right.
eternity.
Right.
So capacitor will, after some time, when my first peak appears, the capacitor stores this voltage throughout for the entire time, irrespective of whatever you are giving at the input,
Got
until
your point.
unless it is less than minus 1 volt. And your sinusoidal signal, it is maximum is 7 volt and minimum is minus 1 volt.
Right, sir.
So one way you can discharge the capacitance is you simply reduce this DC part, right? If this is, you clamp it down to some lower value. Suppose you are clamp it down to 1 volt DC voltage, right? How do you, by the way, give this DC this input voltage? You just add a battery and as a signal generator, right? If you see in any circuit labs, you will have a power supply or some battery, and in series you connect it with a signal generator input. You go to any circuit lab of your college and just check it that how the signal generator looks like. It can give you sinusoidal input, triangular input, ramp input, right?
Right, sir.
So this signal generator in series with this. So if I reduce this battery voltage, then my DC level will come down. This DC level will come down means my this sinusoidal, suppose it is 1 volt, then what happens? My DC level is here, and my signal will then be, it will be maximum 5 minus 0.3, right? Then my signal
Yes.
will be this. The sinusoidal amplitude is not changing, but the DC level is shifted. So in that case, in that way, we can make the capacitor discharge again by making the VI to go less than minus 1 volt. Okay.
Got your point.
So my answer would be this constant equal to this, but this is not the complete answer. After transient means after this time only. This is called my transient. I have explained this in last lecture also, in last tutorial session. What is transient, what is steady state. So during this, after transient in steady state, it will remain at minus 0.3 volt. Okay. So just another problem with a Zener diode. What they are asking, that a simple voltage regulator. I have mentioned that Zener diodes are used as voltage regulators because what is a voltage regulator, by the way? If you see in earlier refrigerators and or earlier televisions, cathode ray tube televisions, right, which did not use these solid state circuits that much, there you used to have a separate voltage stabilizer, right? In that case, you use Zener diode. Or let me put it another way. Suppose you have a AC signal, right? AC signal of say 220 volt, and you want to rectify it. So what will you use first? You will first use a step down transformer to reduce it to some small voltage level, right? So small manageable, I would say manageable voltage level. Then you will use a rectifier, right? Rectifier will have ripples. If you have gone through the rectifier lectures, it will have ripples. To accommodate that, you use filters. Then you use voltage regulators. Then you have your final DC stable output. So at this stage, your Zener diodes are used. So we are out of time, but let's go through this problem very quickly. So what they are asking, that to ensure proper operation, Zener diode which has Vg equal to 10 volt requires a minimum current of 10 milliampere, minimum current of 10 milliampere, and the maximum power dissipation of the Zener diode is 1 watt. Means if this is can anyone please tell me that what is the significance of this circuit? I think this is more important than solving the problem. The significance of this circuit is, you see, this RL is nothing but a load, right? It can be any load. What do we mean by load? Means any circuit. Suppose you have a very complicated circuit, right? You have a very complicated circuit. You can just simply look into the circuit. Suppose you have so many transistors and all. You have transistors, you have this BJTs and whatnot. Many resistances, capacitance, inductors. You have many things. But you look at it and you see the impedance, in input impedance. That real part of that you can model it as RL. So any load means, suppose your refrigerator is working at some high voltage, some low temperature for freezing, quick freezing and all condition, your load accordingly will change. But what happens if you put a Zener diode across it? See, we know that Zener diode has a very it has characteristics like this, right? So what do that mean? That at certain voltage you have infinite amount of current flowing through it. So it preserves this voltage. It preserves this voltage. That means whatever the fluctuation in load is there or the supply is there or it is in there, the voltage across this will remain same. Suppose your appliance is working on this 220 volt AC only, right? Or suppose no, not 220 volt, suppose 12 volt DC only, then it will preserve the state that it should work across 12 volt DC. That Zener across the Zener diode you will have that 12 volt DC. So whatever load you apply, your voltage will be stabilized to that point, right? So to solve this problem, you need to first identify the constraints, right? First thing is your I minimum. I minimum is 10 milliampere. What is your I maximum? How can you find? This is nothing but P maximum by voltage across Zener diode. What is your P maximum? P maximum is 1 watt. What is your voltage across Zener diode? 10 volt. That is 100 milliampere, right? So across the Zener diode, you can have between 10 milliampere to 100 milliampere current. Now the question is, if your input voltage can vary from this, what is the minimum value of R required? What is the R minimum required? So this voltage VRL, say A, no, not say VA. This VA is nothing but your 10 volt for the Zener diode to operate. Proper operation means Zener diode is VA is your 10 volt. Then what is your current through this RL? IRL is, this is IRL is nothing but 10 volt by 1.25 K, that is 6.67 milliampere, right? This current you know, this voltage you know, you need to find out the R minimum. So if you find out your R minimum, what will be that? VI minus VI minus VA divided by current through it, right? So what is the current through it? Let's say this is IZ plus IRL. This is nothing but KCL, right? This current is nothing but sum of these two currents. So you have this condition. VA is your 10 volt. IRL is nothing but 6.67 milliampere. So you need to minimum R min, you need to find out. So your R minimum will be when your IZ is maximum. This is maximum, denominator is maximum. IZ maximum is your 100 milliampere, right? And your V in should be between 12 to 15 volt, because that is the fluctuation level, they are checking, right? So what value of Vi we should take, right? If you take Vi equals to 15 volt, then my R minimum is coming out to be 15 minus 5 upon 100 plus 6.67. This is in milliamps, this is in volt.
So 15 minus 10 or 5?
Oh, sorry, right. Thank you for being attentive. 15 minus 5, that means your 5 divided by 106.67, right? So it is coming out to be 0.46068 kilo ohm. That means nothing but 46.8 ohms, right? So your answer would be 47. Now let me tell you, why didn't I take Vi equal to 12 volt? See, if R is to be minimum, then my Vi can also to be, logically I should have taken it 12 volt, right? But why didn't I take it? This is a condition you need to check while solving this kind of problems, right? Suppose I am taking Vi as 12 volt, okay? Then what will be my R minimum? 2 by 106.67 kilo ohm. That is 2 divided by 106.67. That is your around 19 ohm. Okay. Now see, you have designed your voltage stabilizer in a way that this is your 19 ohm, this is your Zener diode, and this is your input, and say this is your 1.5k, okay, and this VA is 10 volt. Now suppose you have designed and installed your voltage stabilizer using 19 volt. Then what happens to, if suppose my Vi has been fluctuating to 15 volt, let's say Vi has been fluctuated and it is cranked up to 15 volt. Then what happened? What is the current through this? What is the current Iz in that case? Iz can be find out by simply Vi minus, sorry, Vi is my 15, right? So it is nothing but 15 minus 10 by 19 minus this 10 by 1500. That is your Iz is nothing but 5 divided by 19 minus 10 divided by this. This is coming out to be 256 milliampere. Okay. If it is 256 milliampere, what is the power across Zener diode? Iz into Va, that is 256 milliampere into 10 volt, that is 25, no, 2.56 watt, right? Can you comment on this? 2.56 watt, is it allowable?
Max, the maximum wattage was 1 watt, I feel.
Yes, maximum was 1 watt, right? So it is not allowable, right? So you cannot make the design starting with this assumption. Okay, so this you need to check while calculating. By logic, you will feel that why don't I take Vi is minimum? But you take Vi minimum and you design your voltage stabilizer, and suppose you by any chance some spark is there and your voltage is clanked up to 15 volt, and then your this Zener diode will be gone. It is beyond your limit, beyond your power rating, right? So in this way you can check it. So what is the answer? 47 ohm is the answer. Similarly, the last problem, it is asked that what is the minimum value of R for which the circuit would work at desired. What have they changed? Or sorry, what is the maximum value of R? So they want us to find out R maximum. In the similar way, what happens to R maximum? How do we find out R maximum? This R maximum would be nothing but Vi minus 10, Vi minus 10 divided by, this is 6.67 milliampere plus this IZ. What is R maximum for this IZ to be minimum? What is the minimum IZ limit you have? You have 6.67 plus 10 milliampere. So now you need to check using Vi equal to 12 volt. What is the value? Vi equal to 15 volt. What is the value? And if that is violating any of the condition, using this Vi equal to 12 volt, you will get your R max as 2 divided by 16.67, that is around 119 ohm, 119.97, 120 ohm. And this R max would be your 5 divided by 16.67, it is around 300 ohm. Again, if you check that this will be the right answer and this will violate something, this will violate some condition, right? How do you check? Same principle. You design it to this, design it to 300 ohm, use the opposite terminal, use the opposite corner voltage, that is 12 volt, and you check with your conditions. This is your 6.67 milliampere. This is your 10 volt. So what is the voltage through this? What is the current through this? 2 divided by 300. It would be 6.67 milliampere. Okay. So what condition do we violate here? The 6.67 some value, right? So the current through this is 0 ampere. So do we violate any condition here?
The minimum current through the Zener diode should be 10 milliampere.
Exactly, right. So the minimum current condition is valid. Sorry, condition is invalid, is violated. So this should be your right answer, and this is we will not take. So 120 ohm is the right answer. So in this way you can solve the problems, and if you need clarification on anything, you can just comment on the YouTube channel at the time with timestamp that what part did you miss, or you can just use the discussion forum in the course web page, right? So that will be all for today. If you have any further doubts, I think we do not have time. You can just simply post in the discussion forum, right? We'll take that up.
Thank you, sir. Are these recordings available?
Yes, these recordings will be available, and these recordings are uh, wait a minute. These recordings are there in the course web page. You can see that in the course web page they have given the link where the live session of Professor Patil is there, like a left tab where you find the assignments and all. There also you will have these links, right? You will have a
Okay.
Google sheet, and there the links and the this document folders are also mentioned. From there you
Okay.
can access this.
Okay. Thank you so much, sir.
Okay,
Thank you.
thank you, thank you.